right, in this video, we're going to be looking at lesson 5-2, day 1. And so we're going to be looking at a lot of different properties of exponents and radicals. Now, some of these, like what we see here in your first part of your notes, this is all review of stuff that you've seen before. But let's just go through each of these. I'm just going to go through them kind of quickly. Remember that these apply to both integer exponents as well as exponents that are fractions. So that's what they're showing us in some of these different examples. So remember, we have the product of powers, which just tells us if we ever have two bases that are the same, when we're multiplying, we add the exponents. Like over here, we have the bases are the same as our 4, and so we would add the exponents. And 2/3 plus a negative 1/3 would be just 1/3. So we have 4 to the 1/3 power. Quotients of powers tells us if we're dividing and the bases are the same, we subtract the exponents. Now it's important that we do the right orders, where we take the exponent from the numerator minus the exponent in the denominator. So here where we have the bases are the same, we subtract the exponents. 4 minus 2 is 2, so we get 3 squared. We can simplify that further to get 9. The power of a power tells us if we have a value with an exponent and an exponent outside the parentheses, we can multiply the exponents together. So like I have 7 cubed and then being raised to the 2/3 power, we can multiply those two exponents. Now 3 times 2/3 would be the same as 6/3, and 6/3 simplifies to be 2, or you can think of it as the 3's cancel out, leaving us with 2, so 7 squared, or you could simplify that further and say 49. Then we have the power of a product. The power of a product tells us, kind of very similar to the power of a power, that if we have an exponent outside of parentheses, everything that's inside of parentheses, that exponent applies to. So we don't just do it to the one on the end, but we apply it to every single of the pieces inside of the parentheses. So like the example here, we have 16x to the 1/2 power. Well, that 1/2 would apply to both the 16 and the x. Now remember, if you have an exponent that's a half, that means we're dealing with the second root. The square root of 16 is 4, so in reality this would be 4x, and then the x we can't simplify further, so it would be 4x to the 1/2 power. And lastly, if we have a negative exponent, we just dealt with this the other day. If we have a negative exponent, remember to make that exponent positive, we take the reciprocal of the base. So the reciprocal of a would be 1 over a. So a to the negative m power would be the same as 1 over a to the m. Or if we have 5 to the negative 1/2 power, that'd be the same as 1 over 5 to the 1/2 power. Now it became a positive exponent. All right, so those are some properties that you should have already been familiar with. And now let's look at these. These are different properties of radicals. Zoom in here. So here we have the product property, which is, and we did a little bit of this the other day when we had situations like the 5th root of 32x to the 10th power, and we broke it up into 2 roots. Basically, without even realizing it, you are using this property, which basically states if we have two values inside of the radicals, so the radicand, to give the technical term, but if we have two pieces inside the radical that are being multiplied together, we can separate those into individual roots, and then maybe that would help us simplify the expression. Or if we have, like in this one, if we have the second piece there, if we have a times b to the 1 over n exponents, if we have an exponent that's a fraction, remember that fractional exponent would apply to both the a and the b. Then we have the quotient property. So if we're dividing inside of a radical with, and again, if the numerator and the denominator are inside the same radical, we can split that up so that a radical will apply both the numerator and the denominator. Or if it's written like this in the second form here, if we have a over b, then we have raised to the exponent 1 over n, so it's a rational exponent. That rational exponent would apply to both the numerator and the denominator. All right, so we're going to be applying those properties in all of the examples that we're going to be looking at in this first lesson here. So let's look at this first example. You guys have this in your notes. We have 81 to the 5/6 power times 81 to the negative 1/3 power. So what I notice right away is that the bases are the same. So remember the rules. If the bases are the same, we can add the exponents. But the problem is if we're adding exponents and they're fractions, so they're rational exponents, we need to make sure that we have a common denominator. So I can't add 5/6 plus negative 1/3. So I'm going to change that 1/3 to have a common denominator. So I'm going to multiply the top and bottom by 6. So 2/6 is the same as 1/3. Now I can simplify that. So this would be 81. So 5 minus 2 would be 3. So this would be the same as 3/6, which I know that reduces to 1/2. So remember what that represents is that represents the square root of 81. Square root of 81 would be 9. So Writing it as a single rational exponent would be 81 to the 1/2 power. Simplifying it would become 9. And so the property that we used was the product of powers property. All right, so now we're going to use the quotient of powers property to simplify this one. We're actually going to use, so we have an exponent outside the parentheses. So we can apply that exponent to everything inside of parentheses. So the order you do this doesn't matter. If you wanted to, you could simplify inside the parentheses first and then apply the exponent. But I'm going to actually apply that exponent to everything inside of parentheses first. So watch what that looks like. So let's simplify this. Now the x to the 2/3 power, that's going to stay x to the 2/3 power. 3 times 2/3, that's the same as 6/3. Or if you want to simplify that, 6. So again, this would be 6/3. If you want to simplify that further, 6/3 would be the same as 2. So I'll just do that all in one step. And then in the denominator, 1/2 times 2/3. If you multiply the numerators together, we would get 1 times 2 is 2, and if we multiply the denominators together, 2 times 3 would be 6. So we get 2/6, which, yes, that reduces to 1/3. So now we want to simplify this further. I notice that we have a x in the numerator and x in the denominator, so we have the same bases. So we can simplify that by subtracting those exponents. So we would take the 1 in the numerator first minus the 1 in the denominator second. Remember, we have that y squared. And so then 2/3 minus 1/3, the nice thing is they already have the same denominator, so when you add or subtract those from each other, we would have 1/3 as your answer, and then y squared. So it'd be x to the 1/3 y squared as your answer for that second one. All right, so I want you to try these two problems. So with just like the one that we just did, if you want to start, personally I think that's a little bit easier with these. If you want to start by applying that exponent to everything inside parentheses, like we did with example B there, you could do that for both of these problems. Start with that, and then see what can simplify it further. So go ahead and try parts A and B. So I want you to pause the video, so that way you have the opportunity to try it on your own. So actually pause the video, and then hit play when you're ready to check to see if you've done it correctly. Let's see how you did. Let's start with that first one. So in the first one, in the numerator, we have 3 to the, so we would apply this exponent to everything inside the parentheses. So we'd have 3 to the 1/2 power. Now 2/5 times 1/2 would be 2/10. Now 2/10 reduces to 1/5. So that's what I did in that second fraction. And then 3 to the 1/2 power. Can't do anything with that. That's the square root of 3. That can't be simplified. But the 5th root of 32, that's what 32 to the 1/5 power represents. The 5th root of 32 would just be 2. And so that's as far as we can simplify it. 3 to the 1/2 power over 2. So again, for the next one, this exponent only applies to those two variables inside of the parentheses. So the 2a to the 1/3 power, that's going to stay the same for right now. And then the a would be raised to the 2/3 power. And b, if you take 1/2 times 2/3, that's 2/6. And we'll reduce that in a second. So to simplify this, the 2, there's nothing to multiply there, so it stays a 2. A to the 1/3 times a to the 2/3, we would add those two together. 1/3 plus 2/3 would be 3/3, which would just be 1. So you could either write a to the first power or just leave it as a. And then b, the 2/6 reduces to 1/3. That'd be your answer for that second part. All right, so let's look at how we can extend those properties to look at how we can get properties of radicals. Okay, so for this first one, we're trying to rewrite this cube root of 16 x to the 5th. Now the cube root of 16 does not work out nicely. There's no 3 numbers, because 2 times 2 is 4, times 2 would be 8. Okay, so there's no 3 numbers that we can multiply together to get 16. But we could do one of two things here. Now I'm going to show you both ways, but personally, for some of these problems, I want you to start to get comfortable with the second method, because it's going to make your life a little bit easier as far as the amount of work and the amount of time that it's going to take to do these. But here's the first way. That would be doing a factor tree. So 2 times 8 is 16, 2 is prime. 2 times 4 is 8, 2 is prime. 2 times 2 is 4, and both of those are prime. So this one, we have a situation where we're dealing with the third root. So for every 3 of the same, we get to factor 1 out. Okay, so that's the buddy system, so they have to go out in groups of 3. So to simplify this, we would have a group of 3 2's, so it come out as a single 2, and then that other 2, that's left over under the radical. This would be under the third root. Now, what do we do with that x to the 5th? Let's think about that for a second. Oops. So the third root of x to the 5th. X to the 5th means that we have 5 x's being multiplied times each other. So remember what this rule is saying is that for groups of, or they can leave the radical as long as they go in groups of 3, including variables. So that group of 3 x's get to come out as a single x. And we're left with 2 x's underneath the radical, so that would be x squared. Now, I don't want to have to do problems like this. Like, let's say if instead of x to the 5th, let's say if it had been x to the 25th. I don't want to have to write 25 x's down and try to look for groups of 3. That would just take too long. So let's think about an easier way to do this. Let's go back to that x to the 5th. Remember, we have that property, where if we want to write this in radical form, remember we looked at this way, but remember we also talked about it goes both directions. So if we already have something written in radical form, we can write it in exponential form. And so remember we talked about that in the last lesson, where we would just take the power divided by the root. So what I want you to do is I want you to think, how many times does 3 go into 5? So think old school division. So 3 goes into 5 one time, with the remainder, because if we multiply those together and subtract, you don't have to, maybe you can know how to get the remainder on your own, but this would have a remainder of 2. So think about what that means. 3 goes into 5 one time, so we're going to have 1x. Whoop, there we go. We're going to have 1x that's going to come out, and there's going to be a remainder of 2. Think about what the word remainder means. It means to remain behind. It means left behind. So there's going to be 2 remaining under the radical. So whatever the remainder would be stays under the radical. However many times 3 goes into the value, that's what comes out. So let's go back to that example where I just came up with. We had x to the 25th power. How many times does 3 go into 25? 3 goes into 25 8 times. So that means there'd be 8 sets of x's that can come out. And 3 goes into 25 8 times, because 3 times 8 is 24, with the remainder of 1. So there would be 1 that would remain under the radical. So if it was a cube root of x to the 25th power, that would simplify to be x to the 8th times the cube root of x. So that's just a little side note and an easy way to simplify those situations. Now I told you that there was going to be 2 methods that you could use to simplify this. One using the tree diagram, or a factor tree, and this other one using this idea of understanding what a perfect, in this case, a perfect cube would be. So if you can think of a number that multiplied times itself 3 times would give us close to 16, that would be a factor of 16. That's a really easy way to look at it. So the factors of 16, one of the factors of 16 would be 8 and 2. So the cube, remember we have that rule then that the cube root of 8, we could separate that out to be the cube root of 8 and the cube root of 2. The cube root of 8 is 2, so that would simplify to be 2 times the cube root of 2. That's just going to be a little bit faster and save you some time if you can get familiar with that method. So for some of you guys, if you're really strong in math, I would really encourage you to do this alternate method. And I'm going to show you that with these future examples too. All right, so let's look at this next one. So I know it says try it, but let's look at how we'll do these two together just to get some more practice. So the 4th root of 81, a to the 8th, b to the 5th. So what we can do is we can think of this as the 4th root of 81, and then we'll do this separately and just do this in 2 pieces. So the 4th root of 81. Now this is one that actually works out nicely. The 4th root of 81, this is one that you should start to recognize because you're going to see this one pretty frequently. 4th root of 81 would be 3. And now we're going to take each of these exponents and divide it by the root. So 4 goes into 8 2 times evenly. So there's none left over. There's no remaining to stay under the radical. But 4 goes into 5 one time with the remainder of 1. So we would leave 1 under the radical. So 4 goes into 5 one time. So 5 divided by 4 is 1 with the remainder of 1. So the one that remains stays under the radical, and that's your answer. Okay, let's look at the next one. So with this next one, we're going to break this up into a couple of pieces between the numerator and the denominator. So we'd have the cube root in the numerator of x to the 4th y squared. the denominator, we'd have the cubed root of 125x. So let's start with the numerator. So 3 goes into 4 one time with the remainder of 1. And 3 doesn't go into 2 at all, so we can't do anything with that. So in the numerator, we would have x times the cubed root of xy squared. In the denominator, we would have the cube root of 125 is 5, and we're left with the cube root of x. So the cube root of 125, hopefully that's also one that you recognize. Now you might think that we're done simplifying these. Now, what I notice though is, let me grab my highlighter. We have the cube root of x on top and the cube root of x on the bottom. So essentially those two x's would cancel each other out. So if you wanted to see why, that would be the same as having x to the 1/3 power on top, x to the 1/3 power on the bottom. So those would cancel each other out. So our answer would simply be x times the cube root of y squared all over 5. So if you ever have the same thing in the numerator and the denominator underneath the same identical roots, look to see if that can be reduced or canceled out to simplify that further. All right, let's look at these. We want to simplify the 5th root of 16 times the 5th root of 8. Now, what I would do is, so these are both underneath the same roots. So this would be this. So let's just go ahead and combine those. Now, if you wanted to, you could multiply 16 times 8. So if you want to do that, go for it. But for this one, we're going to do the factor tree. I know that the other method I told you would be one that would be valuable to know, but we're going to work with larger numbers here. So let's work with the factor tree for this one. So if I take 16, because if I took and multiplied 16 times 8, I'd get a big number, and I'd be looking then for two numbers that multiply together to be that big value. So don't bother going that method. Okay, so now what we're going to do is we're going to take the factors of 16. What are the factors of 16? 4 and 4. What are the factors of 4? 2 and 2. So that's what 16 breaks down to be. But now we've got to remember to go back and do this 8. 8 breaks down to be 2 times 4. 4 breaks down to be 2 times 2. So what are we looking for? We're looking for groups of 5. So 1, 2, 3, 4, 5. There's a set of 5 2's. So we get to factor out a 2. And then these pair of 2's we can't do anything with, so we just multiply those together. And 2 times 2 would be 4. So this would simplify to be 2 times the 5th root of 4. Don't forget to include the root as part of your answer. That's a common mistake. People just forget to include that.